So here's our last lecture, and today I'm going to keep my promise. I'm going to keep my promise to cut through all the redundancy we had in the sequent calculus and give us a really, really simple system that can in fact be implemented in a single page prologue. Now let me first remind you where we are at the moment. We have all these logical signs. There could even be a couple more, like, I don't know, exclusive or. And that's actually, I never gave you sequent rules for if and only if, did I? They're not very hard to come up with. To do it right, if you want sequent rules for if and only if, remember, you mustn't mention any other connectives. So if you have, for example, implies in your sequent rule for if and only if, you've done it wrong. It's a nice little exercise. So with all these connectives, we have lots and lots of rules because we have two rules for each connective. Maybe those two. Actually, we never had the modal operators and quantifiers at the same time, but you can. So that's an awful mess. So somebody, somewhere, at some point in time, thought of simplifying the sequent calculus by working in negation normal form. Now, as you remember, negation normal form means the negation symbol is only applied to atomic letters. And that immediately means you don't have these annoying if and only ifs and implies, because they have an implicit negation in them. So this has already simplified things a lot. It's got rid of a number of connectives. But the really big win is when you realize that having basically reduced negation to just applied to atomic letters, so it really doesn't exist as an independent symbol anymore. See, I took away negation as well from this list. If you remember your sequent rules, a formula moves from one side to the other only when negation is involved. You can look at any sequent rule where you see a formula moving from one side of the sequent arrow to the other side, and that's either because it was an actual negation there or because it was something like an implies. So once we are working with negation normal form, we will never have formulas moving from one side of the sequent arrow to the other. That means we can get rid of one side of sequence altogether. You might imagine it would be most natural to keep the right side, which is the positive side, and just work in kind of, I want to prove A and B, so I prove A and I prove B, and so on. But somehow people are perverse, perhaps. They choose the left side. So now this sequent calculus, and these are not new rules, so don't freak out and say, I've got to learn even more than before, because you've seen that one before, right? For all on the left, it's the same rule, I just got rid of the formulas on the right. Exists on the left, same thing as before. Same condition for exists on the left as you had before. Again, and on the left or on the left, they are all the same as before. One thing that has changed, so the notion of basic sequent has to change, because remember, a basic sequent had a formula on each side. We got rid of the other side, so we now, like a basic sequent now, is going to have a negation of A and A on the same side. And the cut rule, we never use the cut rule, as you remember, but just in case you feel a sentimental attachment to it, you would have to write it like this. So you might find it a little weird having the sequence with the right side empty, and in fact the empty right side says false. Because remember, the right side is the things we're trying to show, and it is a disjunction. The empty disjunction means false. So in fact, when we use this style of proof, we are basically proving things by contradiction. So if you take a formula that you want to prove, you will have to negate it first, then convert it to negation normal form, and then you find because you've negated it, you stick it on the left side, then you use the sequent calculus using these rules, and basically you've proved it by contradiction. And this makes, if you like, a kind of sympathy or a similarity between this kind of proving in first-order logic and the clause methods we were using, because they also prove theorems by contradiction. And if, by the way, of course, we had modal logic last time, and we don't want to do without modal logic, again, these rules are the same rules as before. We just got rid of the right-hand side. So this is exactly the same. Now you might say, I don't like proof by contradiction. I think it's crazy and indirect. In fact, they do call them indirect proofs sometimes. I want to throw away the left side instead and work with the right side. Do I get a different system? The answer is not really. This magic thing called duality, it's a bit like, I don't know, let's imagine your morning routine. You get up, you know, and you brush your hair, and maybe you clean your teeth, or maybe you shave, or maybe you don't. And now imagine filming that. Now someone else goes and films the exact same thing in your mirror. Is it different, the thing in the mirror as opposed to the thing without the mirror? Well, they're not really different. And in the same way, if you did your right side sequent calculus and did a proof of something, or your left side sequent calculus and did a proof, you would find the proof would have the exact same shape, only for every, or you would use and for every, for all you'd have exists, but it would be exactly the same logical argument. So there is nothing to gain by switching to right side sequence instead. And nobody ever does, at least as far as I've seen. So I have a little example here. So a random formula. This seems to say something about pushing quantifiers in. So we begin with a full first-order logic formula, of course. Now, as I said, we want to put it on the left-hand side. That means we need to negate it first, because remember, a formula on the left has been negated. So we negate this, and what is it? I can try and do it. Has he got enough brains to find a piece of paper, find a pen, and do it? Where's my pen? Is here. Paper is here. Go on. Then remember, when you negate an implication, you assume that to be positive and that to be negative, only I'm not converting to clauses, only to negation normal form. So I take this as positive, and I guess that's going to be for all x. I have to get rid of the implies there, so that will be not p or q. X is what I think that it's going to be. This one has got to be negated. Now again, I'm negating an implication, so I keep that as positive. And p, now finally I negate that, and I get exists y, not q of y. And I hope that agrees with what's here. Woohoo, yes it does. Well, here I can see that I've already split up the conjunctions and made them into separate formulas. So now you put that in on the left-hand side, and this is going to be a sequent proof of exactly the same kind we have been doing before. Excuse me. So what can we do? I got rid of the conjunctions already, so we don't have those to worry about. We have an exists, we have a for all. I hope you all remember we can't do anything with the for all yet because we haven't got any terms to play with. So we go over to the exists and say, aha, I could get rid of this quantifier. And now y is a free variable. And by the way, we are allowed to get rid of this quantifier because there are no free variables at all in the conclusion. So we can use exists on the left We get rid of that quantifier. Now we have a term, namely y, and we being humans can look ahead and say, yes, if I plug in y here, it's going to do something that looks reasonable. So you then do your for all on the left, plug in your y, and the rest comes out fairly straightforwardly. So that is a simple proof in the Tableau calculus. And as I said, so far all we've done is throw away some connectives, throw away the right-hand side of our sequence, and you can see now that the sequence calculus consists of really just those 4 rules that are left. We could do even better, but first we need this. I need to move it there. No one should ever say that you leave here unprepared for industry. Okay. Now remember, every time I show you a new set of rules, that is a new formal calculus, and although these different formal calculi may be related to one another, they are nevertheless different. And so you need to remember which one you are working with at the moment. So now we are changing the game again. This thing is called a free variable Tableau calculus. The idea now is that we are going to regard the variables in our sequence as unifiable. That is, we're going to allow unification. You remember unification, it was only a week or 2 ago. So unification is a cool thing that instead of asking us to guess what to plug in for a quantifier, it chooses something that definitely matches something else out there. So let's consider if we can add unification to the Tableau idea and get a new calculus. So it's called free variable Tableau because now we are going to allow this variable to change syntactically, which is what we have never done before. And now when we look for a basic sequence, we might have a formula not A and another formula B, and now we are prepared to try any unification between a negative formula and a positive formula. And if they can be unified, I mean, apart from you take off the not, obviously. If they can be unified, then you have created a basic sequence. Now, an important thing, I will demonstrate it in a moment. When you do this unification, you need to remember this will update the values of variables, and you need to propagate that throughout the rest of the proof so that your variables are being used consistently. Now, the thing, when I suddenly say that we're allowing variables to be replaced by other terms, you could say, what's going to happen with existentials? Because, you know, when we pull off an existential quantifier, we leave a variable there, and we don't want those to be instantiated, do we? Because that wouldn't make any sense at all. And then we'd actually be treating for all and exist as doing the same thing. So that wouldn't work. So in the free variable Tableau calculus, we need scolomization instead. So we get rid of exists on the left altogether and work with scolomized formulas. And at this point, we have only 3 sequence calculus rules left. That is, for all, and or. And basic sequence, if you want to count that as a rule, but it's... Okay. So here's a little example. What am I doing? So, by the way, this remark is just to remind you what scolomization is. This is not a thing. You can't prove this because it's not a theorem. Reminding you that scolomization is local to each formula. So, for example, this exists here, doesn't depend on, it's outside the scope of the for all. So this exists x, that can just go to a constant, namely a, whereas the exists z here is in the scope of a for all, and that's why that turns into a function. You remember that? We had it before. So why am I doing it this way? This is a totally chaotic way of lecturing. I'm going to skip that remark. I might come back to it in a moment. So let's look at this formula here. I believe we've seen it before. It's one of those weird formulas which is not true in intuitionistic logic and looks kind of unbelievable because it says there's an exists x such that for all y, px equals py. I think we went through exactly why this is a theorem. But anyway, now we're going to prove it in the free variable Tableau calculus. Remember what you need to do. This is also a Tableau calculus. So again, we need to negate the formula first, then NNF, scolamize, and then we're ready to go. So we would negate this thing, and we're going to get for all x exists y, and that'll be, I guess, not px, or, and we need to scolamize, so that'll be p of fy, and I hope that is p of f of x, of course. And so that thing at the bottom is the result of scolamization. Okay, I hope you're with me so far. Now here we are in our free variable Tableau calculus. There's only one symbol available, so I kind of said you shouldn't use for all if you haven't got any terms. We haven't got any terms, but there's nothing else we can do, and it really is not sporting to give up on the first step. So we do it anyway. So we apply our free variable version of for all on the left, and it introduces a new variable. And as I've mentioned from time to time, in most examples when we use a for all, we throw the formula away. That's because I'm too lazy to keep writing out quantified formulas over and over again. And in most of my examples, we don't need to use the formula a second time. But in general, you could use it any finite number of times. And here, in fact, we are going to need it. So that's why I've kept a copy of it. What can we do here? Well, we can split up the and, I suppose, which we do. But now we are, again, we have a for all here, and that is the only thing left that we can do is for all on the left. Now remember, we're using, this is now a free variable Tableau calculus, so I don't have to think and guess a term to plug in. I just generate a new variable. Let's call it z. I can split up the and now this is the weird thing. And this is, if you like, the mystery of, well, it's the mystery of proving a thing when in the beginning you really do have to use for all on the left when you have no idea what to put there when there are no terms available, because somehow now we can prove this. So we did not, actually I should go back a bit. Did we have a basic sequence here? That is, could I unify py and the p of f of y there under the negation sign? And we can't, because there's an occurs check, because y occurs in f of y, and the scope of these variables is the entire, I guess the entire proof, actually, not even the entire sequence, but the entire thing you're working on. So these variables are global to your entire proof, so there's no, you can't do any renaming like you could do with different clauses in resolution. So that is not a basic sequence. And yet, now that we have made a new variable here with the second use of for all on the left, suddenly we've got p of z can be unified taking off the not. We could replace z by f of y, that would do it. Or, taking off that not there and looking at those two, we could replace y by f of z. So we have now two different ways of doing a unification between a positive and a negative formula and creating a basic sequent. And because this is the only part of the proof there is, y goes to f of z, and that closes the whole thing, and we're finished. Okay, and having given you that example, I can now go back to this little aside I had, which was, for some reason, for 10 years or more in the wrong place on this slide. Same example, and I just wanted to remind you again that if you ever get the chance to reduce the scope of a quantifier, you should. So like here, this formula, when I convert to negation normal form, if first I reduce the scope of this existential quantifier and then reduce the scope of the universal quantifier, now when I scolomize, I get a thing where the contradiction is like staring you in the face, right? Because it says for all x p of x and not pa. And if you did this proof in the Tableau calculus, you'd have your for all on the left, and then the very next step would be basic sequence. So you'd get a much shorter proof. Okay, end of aside. Now I wanted to mention, I told you that when you find a basic sequence, you do a unification. Typically you update variables and you need to propagate this variable updating through the rest of the proof. And I've got an example here. So this thing, which is not a theorem, this is not a theorem because this is like if I say everybody here is either happy or sad. That doesn't mean we conclude that either everybody is happy or everybody is sad, does it? So this is not a theorem, and we're not going to be able to prove it. But let's just see how that works out in the free variable Tableau calculus. So looking at how invalid formulas are blocked from getting proved is quite important in understanding how calculus works. So did I figure out how you do this? Well, it's the usual thing. We need to negate. That's an implication. So we take this positive and that negative. So taking this positive, it's already in negation normal form. So we have for all x, px, or qx. That's great. Negating this, we're going to have to push the negations in, and I'm going to get exists x, not px, and exists x, not qx. Which then, once you scolomize the exists x, not px, you get not pa. And for the exists x, not qx, you get not qb. So there's our nice scholomized sequent. This will be a very, very short proof attempt. So there we are. That's what we're starting with. The only thing we can do is unfold the for all. So we unfold it. Yeah, I threw the quantified formula away. Now you might say, well, maybe if you kept it, you could prove it after all. And the answer is, no, you couldn't, and I'm too lazy to try and show that you couldn't, because, I mean, you're welcome. By all means, go in your room and you can spend hours expanding this formula out over and over again and see if you can prove it. And if you can, you'll have just proved that first-order logic is inconsistent, and you'll get a Fields Medal just like that. And actually, that would be the end of mathematics, and your name would be in the newspaper. What can we do now? We have disjunction as our only symbol, so we do a a or on the left, and now we have this one and this one. I think the order in which you tackle them doesn't matter, but being a normal person, I do things left to right. So I have not PA and PY, so again, they have opposite signs, so we can try and unify underneath the negation sign, and we say, okay, set Y to A. At this point, Y has been set to A. Now, if you go over here and you say, not QB, QY, I want to now unify under the negation sign again, and I want to set Y to B, but Y is already, it's been set to A, so you can't do that. So that is not going to work. What would happen if we had more copies of them? I guess the problem is, for it to work, you need to split on a disjunction that will have the same variable, even if you had lots of other copies. Let's say you had the same thing with the Z. You would have to use the same Z here and here. You'd have the same problem. By all means, you don't believe me, I'm not offended. Try it out for yourself. Well, that's there to remind you that people aren't rational. Moving on, I just want to make a few points to be clear here, just to emphasize the Tableau calculus and the free variable Tableau calculus are separate systems. I'm somewhat aware that you guys are shown a whole bunch of things here, and they are all, again, they're connected, they're related, but they're different, and it is quite easy to scramble things up in your mind. So if you like, the free variable Tableau is the one that people like to implement. We saw in a previous lecture, although I believe I called it the model elimination, it is often in its modern form called a connection Tableau, and this is also a thing that some people like to research. Generally, the point is, if you want to build a resolution theorem prover, go ahead. I mean, it's a fairly, I would say, a kind of part 2 project that would keep you quite busy, though I think you could do it. But it's a major undertaking, especially if you want it to be at all performative. The number of fairly sophisticated heuristics and things that would need to be, algorithms that need to be implemented there is much more than I've actually told you about. So you're talking about a really big pile of code to do resolution. But to do a Tableau calculus, or even one of these things called a connection Tableau, which I've not really got into, you can get away with a lot less code. So, for example, now you guys don't know Prolog yet, do you? Well, that's some Prolog. So that is the complete prover. And although you don't know Prolog, I can still somewhat walk you through this to give you some. There were times in the past when you guys were learning Prolog at the same time, and you could even read this a bit. But even so, because I wouldn't go through the exact details of this code anyway, but just to give you an idea what's going on. Now, you'll remember in the free variable Tableau calculus, we have rules for or on the left and on the left for all on the left basic sequent. And what you do when you have a sequent, certainly what this thing is going to do, is go from left to right through the formulas in the sequence, applying those rules, whichever. If it's an and, it will do the and rule, or it does the or rule, and so on. And if it has a thing which is simply an atomic formula, or the negation, a literal, I guess, so if it has a literal, it would compare the negation of that literal with all the other literals and see if it's a basic sequence, and then just keep iterating round and round and round until you eventually either use up all the formulas, which means you've proved the theorem, or on the other hand, when you get a basic sequence and prove the theorem that way, or if you run out of formulas, you can give up. Otherwise, you just keep going forever. And this can be expressed, so we have this predicate, this prologue predicate called prove. So the formula being analyzed is the first argument. The unexpanded formulas waiting to be looked at are here. Literals that you've uncovered are here. This has to do with generating variables, and this is a bound on how long you want this thing to run, or rather how deeply you want it to be expanding quantifiers. And prologue, by the way, the syntax of prologue is a little weird. So comma in prologue means and. So this is the formula A and B, and remember what and on the left does? It simply splits the formula in half. So in the case of we're trying to prove a thing with A and B, it says, okay, split that in half, recursively work on the formula A and put B aside later on in the sequence. We'll get to it later on. And that's and. In prologue, a semicolon is written, or is written semicolon. So that's A or B. And as you recall, for or on the left, you have two separate proofs. So for or on the left, you need to prove the whole thing for A. So this is the A case, and that call to prove will actually represent a complete and terminating proof of the whole thing from A. And if, in addition, you can prove the whole thing from B, then you've done it, you have proved your theorem. Now we've dealt with the and the or. The for all case is kind of evil. And even if you knew prologue really well, I'm not sure I would go through all of this, but basically that's a formula, that's a for all formula. X is the variable, FML is the body, and using some quite evil trickery, a copy is made of the body, a new variable is copied into the body, and finally, because you may need to use your quantified formula again, the entire quantified formula is moved to the end of your list of formulas, so that clearly if you kept it at the head, you would just keep expanding it forever and then you'd loop. So instead of keeping it at the head, you move it all the way to the end, to the tail, and you carry on proving with the body of the quantified formula which you've just plugged a new variable into. And so that was and, or, for all. Finally, if it's none of those, it must be a literal, and there's a further little bit of evil here to find another literal that might unify with it. And if that has failed, you can continue to try and look among the other literals for a unifiable thing. So this is trying to find all combinations of things that might give you a basic sequence. And finally, if that fails, then you take your literal, you shove it aside to be remembered for another time, and you keep going with the next formula in your sequence. So what's funny is, okay, this needs to be given a thing in negation normal form, so it's not if you like, There's a bit more code needed to handle problems in the language of first-order logic, but this is the actual engine that deals with the negation normal form. It is complete. And being complete, remember, complete can be a theoretical property. That is, it will prove it, but only after the sun is turned into a red giant. But in fact, this can prove quite a few things that were regarded as hard for a long time. So it's not bad. Now, I have to say, this must represent 25-year-old research by now. I don't even know if the website for this thing is still up. But the same guy, so they call this lean. This is called lean tap. And their whole idea is what they call lean theorem proving, because instead of writing 20,000 lines of C to get yourself a resolution prover, you write, these 5 prologue clauses and get yourself a complete theorem prover. And they have now connection provers written in. I think they're longer than this, but they are still very compact. And if you did want to fit a theorem prover on, I don't know, a smartwatch or something like that, you would do it this way. Okay, that's it. Thank you very much.